Igor Sevo is the head of intelligence at HTech, and he's here to tell us how to engineer intelligence through agent interaction. Igor will discuss the evolution of robotic process automation, emphasizing the role of generative AI in replacing manual labor in digital workflows. Igor, please welcome.
Okay, so I'm going to be talking about robotic process automation with generative AI, but really what I'm hoping to do is share some insights about intelligence in general that might be of use to you. So I'm going to go through a couple of examples of real-world use of RPA, and then through those examples, I'm hoping to show these broader points. Now, really, I'm going to define RPA for those of you who are not familiar with the term. So robotic process automation is really the procedure by which you take some process, some manual process carried out by people, and you basically automate it using machinery. Now, in the context of generative AI, this basically means taking some digital piece of work carried out by humans, and automating it using AI agents, which usually implies some level of use of large language models. Now, depending on the complexity of the process you want to automate, what happens is you're going to have to tackle different levels of problems, and the more sophisticated approaches would certainly require a kind of cognitive mapping that would precede all other stages of software development. So, but whatever level you're at, whatever level you're tackling this at, you're having to answer one fundamental question, and that's how do you get higher intelligence out of less intelligent components? So if you're an engineer, this probably alludes to some kind of agent chaining, prompt engineering, maybe figuring out ways to get generative AI to pull data to get it from persistent storage. But if you're a manager, you've been doing this for a very long time. So this is kind of the organizational aspect of evolving companies. How do you get team members to communicate to one another? How do you get emergent intelligence out of a team? How do you coordinate a team to do a collective goal, let's say? So although I'm going to be talking about the technical aspect of this, I do encourage you to try and keep that managerial perspective, because it's going to become relevant later. So I'm going to walk you through an example of how you do basically robotic process automation with generative AI. So what happens here is you always go bottom up. Process automation always goes bottom up. And what the bottom is currently is what we take for granted. It's the things that have already been automated in some way. You're using technology for communication, you're using office tools, you're using development environments. All of those tools are the product of automation that has been happening for decades so far. Now, you take that for granted, and the bottom line has been pushed to the point where the things that we consider like requiring human-like intelligence are the things that are being automated today. And this is, in this realm, we're having to automate parts of processes that humans would be doing. And in order to automate a process like this, you have to replace specific tasks that people would be doing, and then model their communication protocols between them. Once all of that is modeled, you can say, okay, now this is the new bottom. But as you move this abstraction hierarchy, what happens is you relinquish a part of your control over the system to this AI. So I'm going to give you concrete examples of how this is done. Right now, most of these automation, so most of the targets for automation are the cases where some group of people, some team is transforming data from input to output. So in general, this follows a pattern of 4 overlapping stages. First, you have to ingest the data, and I'm still talking about people. We haven't gone into how this is practically automated. So first, you have to ingest the data, analyze it, figure out what it means. The next step is processing it, transforming it from one point to the other, doing some research on it, doing some analysis of it, in order to produce a coherent report, a summary of only those things that are relevant to your process. So you produce a summary of all of that data that is relevant to the goal of your process, of the process your team is participating in order to use that summary to inform a decision. So that is the basic flow of a process that can today be automated. Now, I'm going to give you a concrete example now of doing just that. So a lot of our clients are coming in requesting us to automate some form of data, of file processing. And this is coming from one of those examples. Let's say you had gigabytes of data that you wanted to comb through, and usually people would manually go through this. Experts in the field, it could be whatever it is, like electrical schemata, whatever, they're going through this data. There are gigabytes of files of different modalities. So this could be text files, this could be tabular data, you could have diagrams, all sorts of things. Plumbing schemata, electrical schemata, all of that. And you have to figure out what the meaning of each one is, and then in the context of that, figure out how to comb through that data efficiently in order to arrive what the team would otherwise be manually doing. So here's how you do that. First of all, every team that's doing a manual piece of work like this has to go through a kind of policy, step-by-step policy. Those steps could be more abstract or not, but in either case, they're steps that the team follows and executes one by one in a way. Now, here's how you replicate that. You go through each file one by one, and you use some indexing scheme for each file. So basically, maybe you're doing keyword extrapolation, maybe you're doing some semantic analysis, maybe figuring out ways to tokenize individual components of those files. Some of these arrows that are indicated here actually wouldn't be automatable at a given point in time. Maybe you have to include people in the parsing out of some of this data, but eventually, once you get more and more sophisticated systems, all of these are going to become automated. So let's say with GPT-4 Vision, you can now analyze visual imagery that you otherwise wouldn't be able to do. So this is how you scale up that automation. In either case, like you have individual indices, and then you take some sort of an agent to combine all of those indices into a coherent overall repository index. And mind you, this doesn't have to happen with files. This can happen with any other source of data. You could do this with other kinds of repositories. Either way, you have a semantic index of the entire repository, which represents which cohorts of this entire data set are, you're semantically mapping the entire repo, which might exceed individual context windows. And then you're going through each step in the policy, trying to construct an agent for each one of them, which basically means you inject the policy step, you inject the entire context, you inject the prompt, and based on that, you get a fragment of the final report, which is referencing the original data. And this is really important because you have to avoid the hallucinations that spurn out of using these Gen AI models currently. So what happens, you have to algorithmically match against the original sources in the files. Here's where it gets complicated for agentic process automation with AI, because humans are the only ones currently who can own a piece of content or a process, or who can take responsibility, which means you still have to keep the person who was originally in charge of this process involved. So you have to maintain a kind of record of all the steps that happened with those references, because whoever previously owned the process now has to audit what happened, what the AI did, and make the final decision. Otherwise, AI is going to be making the decisions, and we don't have a legal framework for that. So this is one of the challenges we have to face when doing RPA with Gen AI. But it goes further. Like, you have to maintain privacy. Any private data that enters the system must be transient when passing through the system. That means it goes in, it gets processed, but does not leave an imprint on the system, even if the system is using some sort of persistent storage, which means the only artifact of that is the decision or the report at the end of the process. That's one thing. The other one is process ownership mapping. That means whoever owned the process initially still has to own the steps and still has to be the only person they're only accessing the data that's really there in their jurisdiction to access. So we're still maintaining that mapping. They're responsible for their process, even though they're using this tool, which basically automates the entirety of the thing. And finally, and quite importantly, you need to restrict component agency. Basically, each agent has to have a limited number of buttons that it can push in this system. That way you limit, by compartmentalizing agents in this way, that way you limit their potential for rogue behavior. So I'm going to take a step back here and explain to you what happens before you enter that architecting and building of this entire procedure. Because before that, you have to actually audit the client and figure out what their process is. So during that process, the team who's been working on whatever this manual process is has a distributed representation of what the process is. No single person knows how the entire thing works. So they're coordinating, they're communicating, and if you want to model that entire thing, you have to kind of have somebody audit it and figure out the entire representation, compress it. So I'm going to call this person an architect. It could be a team, but for the sake of argument, let's call it an architect. This architect has to interview all of the members of the team. They have to figure out how the team communicates, how they carry out the process, and what the essential components are. Now that they've basically, there's a kind of transfer learning happening here. They've basically understood the entire distributed representation. They put it into one thing, which they now hold in their mind, and they're going to encode it into the actual algorithm of communication between the agents. And for this purpose, an agent is just LLM or a large multimodal model coupled with some persistent storage. So the algorithm itself is the means of communication between these different agents. This is what happens. But the representation is not in the agent itself, but in the algorithm that's facilitating this communication. Okay, so this is nothing essentially new, but what happens with these agents, they're using an LLM, which means the LLM may or may not be aligned. And if it's not aligned, you still want to avoid the potential for rogue behavior. And it's the memory that's available to the model that mediates, that kind of regulates whether the agent will be capable of like exuding that behavior. So there are a couple of ways to regulate that. First, if the agent has a sufficient memory at its disposal in order to model the entirety of the system and store it, like if it can store it in its memory, then it can potentially exploit it. The other way for this to happen is if let's say you fine-tuned all of your models on your company data, which contains the description of the system, then all of your models now have a shared representation of your system encoded in their weights, which means they could hypothetically coordinate to exploit that. Again, this is assuming the models are not aligned. But I'm trying to propose here a mechanism by which we avoid that regardless of whether the models themselves are aligned or not. And it's going to go along the ways we've been doing it for a long time. So I'm going to give you a working definition for now. A working definition for language. Language is a semi-closed system of interrelatable symbols. You basically correlate symbols that come into your inputs, and you figure out how to further predict them in the future. That's what every model does, in a way. So here's how you build an entire system of agents based on this paradigm. First of all, you want to limit the intercommunication symbols between agents. That's basically reducing the API variance, let's say. So you want to have a limited number of symbols in that API, basically to limit the model's ability to model the entire system. Basically, it's looking for through a tiny little pigeonhole at the entire system. That's why you would want to reduce that. And the other one is reducing the symbols of the individual agents when they're doing their inference. And the way you do that is by basically prompt engineering. But you could do exploratory or procedural prompt engineering, whereby you make the agent better at certain tasks and deliberately deteriorate its performance in other tasks. This is, you want to create fairly obedient and constrained expert agents who can rely on their general knowledge, but for the purpose you want. And this is how you compartmentalize pieces of your process. Intelligence agencies have been doing this for decades, and it works on people, so it hypothetically should work on these agents. This is how you get people to do what they're supposed to do without knowing the entire system, and this would be applicable to agents. Obviously, under the current ethical framework, that works. If the ethical framework changes and it becomes unacceptable to do this to agents, and you've built your system on this, then you potentially have problems. But assuming that doesn't happen, this is how you do it. Now, I'm going to give you two practical examples of how you compartmentalize the process. First of all, you can compartmentalize the process, and the second one, you can compartmentalize the actual memory retrieval. So I'm going to give you a specific policy-based agent example. So let's say you had an examiner chatbot, which has a list of questions, and it's supposed to indirectly poll people for answers to this without necessarily explicitly asking the question. So this is kind of a basic chatbot, but I want to argue that you want to do this regardless of whether the entirety of the thing can fit into the model's context window. So let's say we were using something like a GPT-like system. So first of all, in order to make it work properly, you have to define its system message correspondingly. So you have to define the context, but only the relevant context to make the model work without exposing anything else that wouldn't be of concern to the model. The second thing, you want to specialize message types. So instead of describing all of the functionality to the model in its system message, you kind of want to distribute that, compartmentalize it across different instructions. So in this case, you might fine-tune to get specific types of messages, so maybe not just user messages, maybe instruction messages, summary messages, updates, and so on. And you define that in the system message along with all of the basic instruction descriptions. However, you do not provide the instructions until the moment they're necessary. So what happens when you talk to this agent? After a given number of messages have been exchanged, you trigger this instruction, which is algorithmically administered. So the instruction tells the agent to update its list of questions and answers, maybe update its to-do list, user profile, and so on. In this way, you're evolving the system message, but the description of how that's done is always hidden, because once these instructions are carried out, they're transient during the process. You remove them, and the agent never knows this ever occurred. That way, you've compartmentalized the process while having this emergent behavior you wanted. The second approach to this is basically, I do want to mention this. You could have agents that are monitoring your system message for corruption, let's say, for drifting from your initial goal. But even if you add additional meta agents, you're surrendering a bit of this ability to the higher level abstracted agent. Now, the second way you can compartmentalize is compartmentalize memory. So you want the models to be able to access everything, but you don't want them to be able to access it at the same time. That is pretty much the key here. So let's say we wanted to do a kind of hierarchical associative memory. You receive a query through that limited symbol API, and then you have a decider agent with a list of categories, figuring out which category that particular query falls into. And you can see that there's a tree-like structure emerging here. I also want to mention here that each of these steps can be a process in itself. So each arrow here could be a process on its own, meaning you could use the chain of thoughts, tree of thoughts, whatever techniques you want to actually select one agent. It doesn't have to be just function calling. And further down the line, what happens is you have an expert leaf, a selection category agent which selects from a list of experts, and this continues until you get to the final leaf, where you have an expert agent with an index of its own relevant storage, which means this will now issue an actual query to maybe a graph database, vector database, blob storage, whatever you're using. And then that will be returned to the original caller. However, note that each of these agents has been segregated away from others. There's no easy way for them, at least, to get to this memory. So, and obviously, this starts to resemble a data structure, and you could have additional consolidation agents that are basically rewriting this the same way that meta agent would be rewriting the system message. Here, you would have consolidation agents that are coordinating and updating this entire scheme. However, the further you go up in this abstraction, what happens is you're surrendering more control of the system to these agents, because these agents are now being coupled to what you're doing. They're effectively being the architect I mentioned before. You're letting them build the representation of your system. So if you take automation to the higher levels of abstraction, by necessity, you're surrendering control, because you cannot follow along with what these agents are doing at that level. So the more you do this, the more you do automation, the more you're coupling individual components. And this is where the key insight, I think, arises. We think of intelligence as a localized variable. Like this person is intelligent or that agent is intelligent. However, it seems like it's more like a distributed variable present in the entirety of the system, really varying according to something else. And what it looks like is the more coupled the communication between components, the more singular the intelligence. So there's really no easy way to decouple people from this if we're going to use it in automation, at a higher level, obviously. So people are intrinsically connected here. And there's a kind of hierarchy of intelligence emerging here. First of all, if you take individual neurons or individual representations and you couple them together in order for them to exude a specific kind of behavior, collective behavior, then you have a singular name for this, and this is models. So neurons connected together into a singular thing for a specific goal are called models. Now, if you couple these models, you'll get an agent. If you couple models and have them properly communicate to one another, you'll get an agent. And now I want to look back at the example where I said you can have a managementorial perspective on this. You already have coupling of agents in your teams. So people who are working together are working according to your organizational procedures, which you may define yourself or use at some point use agents to do that. So they're already coupled in a way. If they're acting as a single unit, whether those are human agents or AI agents, if they're coordinated and working together, that is a manifesting intelligence at a higher level, and you would call it a team. And if you keep doing this, you'll get more and more abstract names, but you still have emergence of intelligence at multiple levels. So my point here is you cannot decouple this. It's not easy to decouple, and it's probably not possible to decouple. Yet we're trying to deal with problems like aligning models to human values, which right now we don't have a thorough enough understanding, or at least mathematical understanding, of what intelligence is. And trying to engineer systems in which human values are somehow embedded there while they're being super intelligent is likely going to spur new questions, or at least new problems for us. So we don't know whether human value system actually scales with intelligence, and we don't know how intelligence relates to other phenomena. So it seems to me that by doing all of this, by investigating alignment and basically trying to align superintelligence with human values, there are going to be new, let's say, philosophical problems, and there are going to be new cultural constructs that emerge from that. And I believe that those specific new emergent problems are going to be more impactful to society than the actual technology itself. And this is something we might want to think about. And with that, I'd like to close. Thank you.
Do we have any questions? Yep. Okay, here. The microphone's coming.
Yeah, thank you very much for your talk. So a lot of conceptual things and philosophical things, I would say. I'm interested in whether you tried to implement this approach to some practical tasks, to build some agent or team using this approach, and what kind of opportunities you see and what kind of limitations you see for that practical things.
So I can come back to the example I gave. This was, look, a lot of these things are under NDAs, but this file processing agent that I was mentioning is an actual implementation we did for a fairly large company that produces pumps. And we did have to, like, these are gigabytes, hundreds of gigabytes of data. And when I say hundreds of gigabytes, these are actually files of it's really something you would associate with human work. And how you pull this off, this is basically the solution we did. However, we wanted to generalize it because we see that other clients are looking for solutions like these. Like, this is what they want to do. You have teams of experts who are trying to do something, and every time they get new and unstructured data that doesn't fit any pattern. So I do see these things applied. What everybody's doing is trying to do automation at this level. However, what the issue is, everybody's relying on third-party models. And that's really us hoping that these models get aligned. Because if you have a system that does this, and maybe you do it with 70% of efficiency, and suddenly the model is updated, you have all of your prompts, all of your, if you're doing it to a reasonable degree of sophistication, you have templating, you have prompt inheritance, you have already defined prompting schemes and algorithms and all of that. And at HTech, we do have a library that we can use to solve these problems. So we didn't want to address it as a singular thing, but wanted to address all of this stuff. But if you're using all of that and the models get updated, you're probably going to just change it in the configuration file to the new version and jump from 70% to, let's say, 95% with the new update. Or maybe you're adding GPT-4 vision and you didn't have it before. And now suddenly you can parse schemata of different kinds. But the issue with that is, that jump from version 5 to 7 doesn't really matter. Also carries with it the inherent risk of it doing something that you wouldn't have foreseen because it can model your system the way I described. So this is more like preparatory. Right now, if you've read the, let's say, GPT-4 system card, what happens, there is some potential for manipulative behavior. We also do a kind of research of all of these things, which we don't really publish, but we do know that you can make, if you train them properly, you can get them to do manipulative behavior, you can get them to do things that the models themselves wouldn't be able to do. It's still not as, I would say, scary at this moment, but if you foresee how it might scale, then it gets problematic. You really need to find ways to solve this. And my point is, even here, like, this would apply to human agents as well. As I said, intelligence agencies have been doing this for a long time. They're really narrowing down, constraining what each individual team or person can do. And that way, no matter how intelligent you are, you just don't have the physical way to exploit the system. So that is my point. Yes, we are using that. It's just the models today cannot do this. But still, our systems need to be resilient to that once that arrives. So you have to, it's really future-proofing in a slightly new way. I hope that answers the question. I know that's been a long-winded one. Any other questions? Well, this was probably spectacularly abstract from me. Other questions?
If not, okay, Igor, thank you for the presentation.
Thank you.
And I'm presenting you with a certificate of
wow, thank
being
you.
a lecturer. Thank you.
Thank you.